Welcome to MEM07005, Perform General Machining. This lecture is a supplement to your student workbook and other resources made available to you. Make sure you have a copy of the participants workbook for this unit. It will help you complete the online quiz and reference the theory covered in the lecture. In a previous unit, we looked at machine tools in general. Now we're going to delve a little deeper into the processes of deciding the appropriate machining processes and in what order these machining processes are performed. Before we begin, just a quick reminder of some of the resources that are available to you as a student. If you don't have access to Microsoft Office, LibreOffice is a good alternative. It's free and available for all major operating systems. Just a reminder, with LibreOffice and Google Docs, you can actually directly edit PDF files and create PDF files. If you have a Google account, you have access to their cloud publishing applications like Docs, Sheets, Slides, etc. All you need is an internet connection. Your participants workbook, as well as other resources, are available to you from Moodle. Moodle has a mobile app which you can download for your favorite mobile device. All the Pertec documents referenced in this lecture are available from pConnect. If you don't have access to pConnect, all the documents are also available from Moodle. Any Pertec components discussed in this lecture are all referenced from the Pertec catalogues and the Pertec website. The recommended textbook for this unit is the Fitting and Machining Trade textbook. The Fitting and Machining textbook can be purchased from Hare and Forbes. You can get it from their online store or in person from one of their showrooms. The link to their online store is available from Moodle and it's on the slide. Cutting Edge Engineering is our featured YouTube channel for this unit. Colin goes into great detail repairing and refurbishing hydraulic equipment. The link to his channel is on the slide and is available from Moodle. Before we do anything, we think, plan, do, review. Let's look at the main lecture. Section 1, Order of Operations. Sometimes the order of operations is obvious. In this example, we understand that we need to drill the hole before we can tap it. And sometimes the order of operations is not so obvious. Machining this V-pulley out of operation could have catastrophic consequences. We need to ensure that when we are machining a component or manufacturing a component, that it is fit for purpose. It is important that a V-pulley runs true to minimize vibration and wear on associated components. The pulley starts off as a casting, which is not accurate or symmetrical. So we want to avoid the number of times that we move the casting from machine to machine. It will be unlikely if we drill the hole in one machine and turn the V groove in another machine that the bore and the groove will be concentric to each other, as we're holding from a rough, unmachined surface. Our pulley started off as a casting. It is not unusual for large and small holes to be created during the casting process. The concentricity on our particular pulley is 0.1 of a millimeter. There is information from the machinery's handbook and the SAE standard for V-belts has been referenced. The maximum allowable run out for our particular pulley is 0.1 of a millimeter. This will increase as the size increases. Don't forget about axial run out, or sometimes known as wobbles. This has to be taken into account also when working out order of operations and machining strategy. A pulley has a maximum run out on a diameter of 0.1 of a millimeter and maximum run out on the face of 0.25 millimeters. Let's plan the order of operations for machining our V pulley on a manual center lathe. If we were manufacturing this pulley on an automatic lathe, a turret lathe, or a CNC lathe, the order of operations would still be the same. Operation 1. Turn and bore side 1. I am clamping off a rough casting. It may take a few repositioning attempts to get the casting running reasonably true. If I can't get the casting running reasonably true, I might have to use a 4-jaw independent chuck. Operation 1, step 1.1. Drill out the hole and make some room for the boring bar. Operation 1, step 1.2. Finish bore the hole to the correct size, tolerance and surface finish. Operation 1, step 1.3 and step 1.4. Machine the V-groove and machine the faces of side 1. We finished bored, faced and cut the V-groove without removing the part from the chuck, thus ensuring all machined surfaces are running true. Operation 2. Turn side 2. Operation 2. 2.1. I've reversed the jaws and located the pulley of the machine diameter and face. The only error that will be transferred to the pulley now is the one from the chuck or the machine. I deliberately machined the non-critical feature on the second op, so any error will not affect the pulley operation. Expanding mandrels. Using the reverse jaws or a fixture on the lathe for the second operation is not our only option. The expanding mandrel is a close relative of the collet, but designed to clamp on the inside rather than the outside of material. These are available as direct mount to the machine spindles or shaft mounted for collet chucks and regular chucks. An expanding arbor is another option. These arbors are pressed into the component that we want to machine and held between centers. Expanding arbors can be purchased in sets or individually. They come in many different designs and configurations. Operation 3. Broaching the keyway. I'll be using the bored out hole in the pulley to locate the broaching bush. Broaches are pressed or pulled through pre-machined holes to transfer the shape of the broach onto the part. Broaches can be purchased in sets or custom made. If we don't have a broaching tool, we can mount a profile tool in the lathe tool post and use a shaping motion to cut the keyway. This is done by locking the headstock and moving the tool back and forward with the lathe carriage. If we're using this method to create the keyway, this step would be included in Operation 1, as we don't want to remove the casting from the chuck until all the associated operations are complete. Operation 4, creating the tapped hole for the grub screw. Operation 4, Step 4.1. Drill the hole for the tapping operation. Here I made a drill jig using the bore and one of the faces of the pulley as a location to ensure that the hole is perpendicular to the bore. The hole is positioned 180 degrees from the keyway, so I incorporated a key in the drilling jig to make sure that my hole is in the correct radial position. Operation 4, Step 4.2. Chamfer the hole. Operation 4, Step 4.3. Tap the hole so I can fit the grub screw. Operation 5, Step 5.1. Degrease and prepare for painting. Operation 6, Step 6.1. Paint the pulley. Section 2. Setting up machine tools. Before we proceed, it's important to remember, if you're new to a particular machine tool, familiarize yourself with the equipment. Do some practice cuts before committing your material. Before we start machining, we need to make sure that the machine is in appropriate condition to start cutting. Is everything aligned? Is everything adjusted? We'll be looking at setting up lathes and mills and drills in this lecture. But the same approach and philosophy applies to all machine tools. The first machine tool we're going to look at is the center lathe. Here, I will be checking to make sure that when turning between centers, my job is parallel. I am not the only user of this lathe, and I'm not sure what has been set or unset by the previous operator. I will be turning a hydraulic push rod and it needs to be parallel. I could use either a faceplate and a center, but in this case I'll be using a chuck with a mild steel center. I prefer this method as it gives me a chance to skim the taper and ensure that I'm running concentrically with the chuck. In this example, the bar is tapered. Is the tailstock offset, or is there a problem with the carriage? There are two ways to check for this. The first way is to do a test cut, then measure each end. We work out what the difference is, we adjust, then we take another cut and measure again. Take note that I've used a dial indicator to reduce the number of iterations and be precise with my adjustments. The second method is to use a precision ground bar or rod that I've measured and made sure was parallel. I place the bar between the centers and run a dial indicator along the length and adjust if necessary. If you still have a taper after taking the first cut, there could be a problem with the lathe carriage or the bed. Use a dial indicator to compensate with a tailstock, or have the machine repaired if you can't compensate for the error. Even if you are using the chuck with tailstock support, a misaligned tailstock can still cause tapers, concave and convex profiles along the length. Check for parallel and flexing with a precision bar. You may have to use a steady if the bar is too long to eliminate any flex. In this example, the steady is utilized to minimize the flex and for the material deflecting from the tool. In this example, my rod is supported at the end with a steady. I don't have a tailstock in there, and I'm turning down the OD of the end of the shaft and threading the end of the shaft. If we are using the tailstock for drilling, reaming, etc., it needs to be on center. Any offset in the tailstock will cause the tools to cut oversize. Other problems when it comes to turning could be run out of the main spindle, run out or damage of the jaws. If the chuck jaws are worn or damaged, we can regrind them using a tool pulse grinder. The grinding is performed in situ. Be aware that the jaws are probably case hardened, so once you grind through the hardening, they'll be relatively soft and require frequent regrinding. Lathe chucks can be purchased with master base jaw configurations, which use soft jaws which can be easily machined or reworked using a standard boring bar. Cutting tools need to be set on center. This will ensure that the cutting tool will perform at its optimum rate. The tailstock is commonly used for setting the tool center heights. Measuring the distance from the top of the compound slide is also often used to set the tool center height. Tool center heights can also be preset using quick change tool holders. Drills and drilling machines. Squareness and runout are important factors to take into account when using or setting up a drilling machine. An out of round spindle or running out spindle, drill chuck, or even a slightly bent drill bit could cause problems with hole locations and size. Holes not lining up on assemblies could be caused by drills not being at 90 degrees to the table. Most drills enable adjustment of perpendicularity. Here I'm using dial indicators to measure spindle runout and drill runout, and I'm using an engineer square for check for perpendicularity to the table. What condition is your work holding equipment in? Are your drill vices in good condition? Do they bend or warp or dislodge the component when they're locked into place? Are the drill vices square, straight? These need to be checked also, as these errors transfer to the workpiece. Milling machines. Spindle squareness and runout are also issues that affect milling machines. An added dimension to the milling machine is the ability to move the table in various directions. Our work holding devices and workpieces need to be aligned to a specific axis of the machine. Pictured above is a magnetic base and dial indicator used to align the milling vise. Pictured here, we can see a scribing block and feeler gauges used to align the milling vise. An edge center finder is also commonly used with paper or feeler gauges to align workpieces and work holding devices on milling tables. Pictured also is the edge center finder you made in year 1. Sometimes the workpiece is used for alignment, not the work holding device. Another common tool for alignment or referencing is the electronic edge detector. This closes the electronic circuit and a little light comes on once the ball at the end of the probe touches a bit of metal. Section 3, cutting data and machining calculations. Feeds and speeds. The two important factors which determine a cutting operation is the speed in which the tool or the material rotates and how fast the tool is introduced into the material.
The speed in which the tool rotates is specified in revolutions per minute. The speed in which the rotating tool is introduced into the material is called the feed rate, usually specified in millimeters per minute or millimeters per rev. Pictured is a feed rate selector table from a center lathe. We can select thread pitch for metric screw cutting and threads per inch for imperial screw cutting. We can also select feed rates in millimeters per rev and inches per rev for general turning applications.
Cutting speed. This value is supplied by the cutting tool manufacturer, specified in meters per minute or feet per minute. The RPM and feed rate values are derived from this value. Looking at the value of 1 meter a minute, 1 meter of material passes beneath the tool in 1 minute. As you can see, with the shaper, it's easy to visualize the cutting speed in meters per minute. As with a bandsaw, the cutting feed is directly input or set in the machine from the data sheet. With a rotating tool, a formula will need to be used to convert that value, that is cutting speed in meters per minute, into a speed that we rotate the tool, which is RPM, and the feed rate in which we introduce the tool into the material. We will be looking at those formulas later on in this lecture. Here's an example of recommended cutting speeds for high-speed steel tools for various materials. This is a generic table. Make sure that you get a copy of the recommended surface speeds from your tooling supplier. And of course, we can reference recommended surface speeds for different cutting tool alloys from the Machinery's Handbook, if you have a copy. Here we can see from our previous shaper example, we would set the feed rate of the tool at 18 to 24 meters per minute. In this case, the tool is not rotating, so the cutting speed and the feed rate are the same thing. But if the tool was rotating, like if this was a milling machine, we would have to use formulas to derive the RPM, which is the revolutions per minute, and the feed rate, the speed at which we introduce the tool into the material. Let's calculate the RPM, or the revolutions per minute. So we're going to convert that linear value, which is meters per minute, into revolutions per minute. On the left, we can see the original formula. We'll be using the simplified formula on the right, which is derived from the official formula to make our life easy. It's very easy to remember. Let's have a look at some examples of calculating the RPM from the surface speed. Let's calculate the RPM of a 10mm drill bit, drilling mild steel. First, let's multiply the surface speed from the tool data sheet by 315. We then divide it by the diameter of the tool to get our revolutions per minute. With our formula, there is no need to convert units. Just input the surface speed in meters per minute and the diameters in millimeters. In this example, 315 times 24 divided by 10 is approximately 756 revolutions per minute. If I had a drill press with a limited speed option, I would pick the closest speed to 756 revolutions per minute. Here we can see the difference different cutting tool alloys make. In this example, the same tool made out of carbide has to be rotated at 3,900 revolutions per minute. Pictured here is an example page from the Machinery's Handbook showing recommended surface speeds for high-speed steel tools. Note in this particular example the values are provided in feet per minute. Using lookup tables to calculate RPM. Let's use this example from the Fitting and Machining Trade Textbook. In this example, we're going to look up the RPM for drilling steel with a 10mm high-speed steel drill bit. Where the alloy, surface speed and diameter lines intersect, that will give me my RPM. In this case, 1200 RPM. Here we can see if I change the cutting tool alloy, in this case change high-speed steel to cemented carbide, our RPM is now 4,000 revolutions per minute. We've calculated how fast to rotate the tool. Now we will calculate how fast to introduce the tool into the material. This is commonly referred to as the feed rate. We first need to calculate the RPM. In this example, it's 3,280 revolutions per minute. Introducing another formula. Feed rate in millimeters per minute equals RPM times number of teeth on the cutter times chip per tooth value. In this example, 3,280 RPM from our previous formula times 6, which is the number of teeth or flutes on the cutter, times the chip per tooth value from the tool's data sheet or from the Machinery's Handbook. In our case, it's 0.1, which is a good general rule of thumb starting point if you don't have a data sheet. So 3,280 times 6 times 0.1 equals 1,968 millimeters per minute. Always refer to the cutter's data sheet for recommended values. Another general rule of thumb, plunge rates are usually half the lateral feed rate. Milling cutters come in various shapes and sizes. Not all cutters can plunge on their full diameter, like an end mill. But an end mill can feed faster through the material due to its having extra flutes. Whereas a slot drill can plunge to its full diameter, but feed slower through the material because it only has 2 flutes. The uni mill is the best of both worlds. It has 3 flutes and the ability to plunge to its full diameter. Revolutions per minute and feed rates when turning. The D value in the formula is the value or the diameter of the part that's rotating. For example, in a milling machine, the tool is rotating, so the D value will be the diameter of the tool. When turning, the D value will be the diameter of the material that's rotating. Irrespective of the machining operation, we're still going to derive our RPM and our feed rate from our cutting speed. Feed rates for lathes are based on the tool geometry and the tool radius. In the absence of a data sheet, a rule of thumb, roughing is usually 30% of the tool radius per rev, and finishing is about 25% of the tool radius per revolution of the spindle. There is no doubt that indexable throwaway inserts are convenient and efficient, and now cost effective, as it eliminates the need for large tooling inventories or specialist sharpening machines or personnel. One tool holder can accommodate inserts for various operations and materials. This goes for milling, drilling and turning. Depending on the configuration and orientation of the insert, some inserts can have up to 8 cutting edges. Carbide inserts are manufactured using a sintering process where the material starts off as a powder and is compressed under high pressure and temperature to form the insert shape. One of the main alloys in the sintering powder is tungsten. It can be traced back to the 1700s, where it was first extracted from the ore wolframite. Other alloys are introduced into the powder, or the sintering powder, to improve things like toughness and hardness. The use of carbide tools exploded during the Second World War, giving the Allies a massive manufacturing advantage as the cutting edges stayed sharper for longer and the tools could be driven a lot faster. Carbides, or carbide tools, come in various grades and configurations. Here we can see the standard ISO color coding identification system for carbide inserts. In this example, P is for steel, which is blue, K, red for cast iron, etc. Here we can see each designation is numbered 0 to 50, increasing from hardness to toughness. If I was machining a very hard steel, I'd select a grade from P1 to P10. If I required toughness, for example a intermittent cut, I'd select a grade P40 to P50. How are the milling and turning inserts identified? As with the grades of carbide, the actual geometries and shapes are also standardized in the ISO system. Here's an example of the ISO designation for insert geometries and sizes. I grabbed this pack of inserts from my lathe. Let's go and have a look at an example. Let's have a look at my example here. The first letter is C, which is the shape. The second letter is the clearance, obviously dictated by the material that I'm cutting. The third letter is the tolerance. The fourth letter, which is important, is the shape, the chip breaker and the geometry of the insert. The next value, which is 12, is the length of my cutting edge. The next one, 04, is the thickness of my insert. And 08, already discussed this, the radius of the tool, it's which the feed rate is derived. In this case, it's 0.8 of a millimeter radius on the insert. I need to order some replacement inserts from my favorite insert supply, which is Kennametal. Obviously, I'm using their catalogs, and I'll be using their catalogs in this example. I'm going to be machining a steel casting. It's going to be pretty tough. It's an intermittent cut, so I'm looking at a grade P20 to P30. Remember, this is an ISO designation. I can quote this P20, P30 to any tool or insert supplier. I found this insert comparison table on the internet, and I use it to compare grades and prices of inserts. In this case, I found my KC9 125 grade, which is a P20 to P30 ISO designation. According to my comparison table, that particular grade's obsolete, and the closest grade in the new range of Kennametal Beyond inserts is the KCP25, so that'll be the Kennametal grade that I'll be purchasing. My old insert's obsolete. They've given me a new grade of insert. I better check and make sure that there's been no changes in the cutting speed, depth of cut and feed rate. So here we go. We got according to the table, is 275 meters per minute. That's my surface speed, and I'll need that to calculate my correct RPM. Again, this is a turning operation. The depth of cut, as per the data sheet, is 1.8 millimeters depth of cut, and the feed rate is 0.4 millimeters per rev. That's the recommended feed rate per revolution to introduce the tool through the material. Always refer to tooling manufacturers' data sheets for correct cutting data to get the best efficiency and value for money out of the cutting tool.